So, hello everybody and good morning. Hope you're all doing well. And in case you're in far Asia or in the US or in South America, so it's, I guess, good evening. Welcome to today's webinar. My name is Omar and I'll be presenting today's webinar to you. Thank you all for taking the time to join us. And I will do my best to make it worth your time and to ensure that you got the most out of this webinar. So, as you see here on the screen, today's webinar will be about battery-operated mesh. Before we start, just some general rules. Today's webinar is scheduled for about 30 minutes. I'll try to keep it short and precise. And to answer your questions, we will have a 10 to 15 minutes Q&A session, which will be handled by my colleague Fuda. So as you can see to the right, there is a chat window. So please feel free to introduce yourselves there. And you can also post your questions there, which will be answered at the end. And in case you have a colleague who couldn't attend with us today, just please remember that we will post a recorded version of this webinar on our website so that you can get back to it and view it again whenever you want. So for today's agenda, we will be touching on a number of important topics here concerning battery-operated mesh routers. Like what benefits will I gain when I choose battery-operated mesh routers, and how does it actually work? And of course, as everything works in RF, what are the certain trade-offs that I should be aware of? And I should keep them in mind before designing my network. And then when you know that there are trade-offs, then there must be also a design guideline, which will help me ensure I design my network in a good way from the beginning without having to do much trial and error. Another important parameter is how does it perform? How often can I send packets? How long will my battery last? So I will do my best to answer all these questions. Plus, I'll also present you with the design guideline to give you an estimate about what performance you should expect from your network under certain conditions. So, to start from the beginning, what are battery-operated mesh routers? First of all, the main difference between a leaf node and a mesh router is that a leaf node goes into sleep mode in idle times to save power. Therefore, a leaf node cannot be responsible for routing packets up and down the mesh. But on the other hand, mesh routers are always on, so they are more suited for this routing functionality. So the new thing here is that now we have mesh routers which still perform the routing functionality, plus they can also go to sleep in idle times. So it's like basically presenting the best of the two worlds. But the important question here is, how does it do that? But before we get into that, why are battery-operated mesh so great? Well, first of all, it can be deployed anywhere without having to worry about preparing or extending power cables or infrastructure. Which means when you don't have to worry about infrastructure, then it means that you can have a very short deployment time. And contrary to some LP1s, Radiocrafts RIIM actually is suited for bidirectional communications without exceeding duty cycle limitations. And last time, since it's a mesh, then range can always be very easily extended for up to 28 hops. When you look here at this coverage comparison, you can see that from the orange dot to the green dot in LP1s, it takes a certain amount of energy to cover that link. But on the other hand, to the right side with the mesh, the idea of hops reduces the amount of energy consumed by each device. This is, of course, because mesh uses the concept of multi-hops. So this means that mesh can give you the same range and maybe also more, but by using less energy per sensor device. Actually, according to our calculations, one transmission of 20 bytes requires 260 to 500 times less energy compared to LP1s. And now to the fun part. So how does all this magic actually happen? Well, the secret behind battery-operated mesh routers is the implementation of TISH technology. And to be more specific, it's a special variant of TISH called receiver-based TISH. So TISH stands for time-synchronized channels. It basically means that all nodes in the network are synchronized in time. The border router sends out beacons which contain this timing information to allow nodes to synchronize. And in case of any shift in time, child nodes always correct it to get back in sync. In receiver-based TISH, time is divided into a series of repeated time slots. Each time slot is 40 milliseconds long. So the idea here is that a node's radio does not have to be on all the time. Instead, the radio is only on in the time slots assigned for this node for reception. In other times, the radio is switched off to save power. Transmitter nodes use a special algorithm to calculate at which time slots does the receiver node turn its radio on. To better understand this concept, let's examine this simple example in the figure with only two nodes, A and B, and only two time slots, as you can see here, first time slot and next to it the second time slot. Let's assume that node B wishes to send the message to node A. So node B uses that special algorithm to calculate when does node A turn its radio on to listen, because as we said before, the radio is not always turned on, it's only turned on at assigned time slots for this node. So node B calculates at which time slots will node A be listening. Let's say, for example, that node B deduces that node A listens in the second time slot. But on the other hand, node B itself listens in the first time slot. So in time slot 1, node B, it's assigned for node B for reception. So node B will turn its radio on to listen. However, to save even more power, node B will only listen for 3.5 milliseconds. If no incoming messages are detected, it will turn its radio off and get back into sleep mode. So this shows that a node does not know that in its assigned time slots, it will receive packets. It just knows that it should open its radio to be ready for reception. And when this time slot happens, it opens its radio for 3.5 milliseconds. If no packets are received, it switches the radio off again. Now, in time slot 2, node A will do the same. It doesn't know if it will receive at that point or not. So node A will turn its radio on. But this time, before the 3.5 milliseconds are over, node A will detect the incoming message from node B So it will, of course, keep its radio on to receive the whole packet, which a packet is around maximum 22 milliseconds. And afterwards, node A will reply with an ACK, which node B will receive in the same time window. So this was, in very briefly, the basic idea behind receiver-based dish and how it works and how the routers switch off their radio to save power and then turn it on at assigned time slots to listen for incoming messages. And if there is a message, then it will keep the radio on to receive the whole message. So as you can see, this mode of operation would have some trade-offs. It's important to discuss these general trade-offs, which will always be there, no matter what design you choose. So there are basically a number of network parameters to tune. For example, this listening time slot occurrence for a certain node. If you choose to make it very frequent, which means that a node turns on its radio for reception very frequently, and also you choose to have a network that forms and has all nodes joining very quickly, this will mean that much throughput will travel through the network, but it will also mean very high battery consumption. So we will always have this trade-off between the network formation time, the maximum throughput, and the battery consumption. If you can tolerate lower throughput and higher network formation time, then you will have the maximum battery efficiency or the longest battery life. And the opposite is also true. So to clear this thing about trade-offs and to make it more simple, to help our customers approach network design in an easy way, we created this simple guideline. It's not supposed to act as a 100% precise predictor of how a network would perform, as this really depends on many things. It rather acts as a rough indicator on what to expect and what to ask of your receive-based dish network, what to ask it to do and what not to ask it to do. So the guideline goes as follows. It's very important to ask these questions. First of all, how many nodes am I planning to have in my network? How often do I want my sensor nodes to send data? Then from these two answers, you can see how many packets will reach your border router per minute. Why is it the border router? Because when you think about the mesh, then you can obviously see that the border router will be always the bottleneck. It's receiving packets from all the networks. So the biggest load on the capacity of a device is always at the border router. So if you think from the perspective of the border router, then that's you can say the worst case scenario. Then anything after it will be easier. So again, how many nodes am I planning to have? How often do I want my sensor nodes to send data? Then from these two answers, you can see how many packets will reach the border router per minute. Then, using this table that we prepared, you can decide which setting to use, which will best suit your application. So basically, we have receiver-based dish on 3 settings. A setting that provides the maximum battery, which is the maximum battery settings. Then a standard setting, which is more of a balance between the two, and then the maximum throughput setting. In case you calculate the number of packets reaching your border router and you realize it's too much, then you can either design for fewer nodes per network, or you can adjust to send data less frequently. And then, of course, based on the average current consumption, you can calculate your expected battery life. I'll give you more examples about that design guideline, but let's first check this graph. This graph shows the relation between the three settings and how they perform and the average current consumption. So as you can see here, in the maximum battery lifetime setting, current consumption, which is the horizontal blue line, is at its lowest. It very slightly increases as you increase the number of desired packets to reach the board router. The x-axis is the number of incoming packets to board router per minute. It increases to the left. So as you increase the number of incoming packets, the average current consumption very slightly increases. However, this can't keep going on forever, because as that number of packets exceed a certain limit that we calculated, if you still continue using the maximum battery lifetime setting, the packet loss rate will be too high for reliable communication. Therefore, you will have to switch to the standard setting. So what's different in the standard setting? The network parameters are tuned to have more throughput. It's designed to handle more throughput. That's why it will better tolerate the higher number of packets, and it will not produce that same packet error rate. Then the same concept repeats. You can keep increasing the number of incoming packets as you go left, till a certain point where the packet error rate will become too high for the standard setting. So you will have to switch to the maximum throughput setting, which is tuned to support the maximum number of packets reaching the border router. So all parameters in this setting are tuned to support this high capacity. And then till a certain limit, then if the number of incoming packets increases, then we enter into the zone where it's not suitable for battery operated mesh anymore, and then using standard dish, which consumes around 900 microamps, is probably better, because yeah, you can handle more throughput, but then you will enter into the zone where it's not battery operated anymore. It doesn't make sense. At this scenarios, then the standard dish, not the receiver, but the standard dish would be the better solution. So here we have some examples for the design guidelines. Let's assume that we have a network of 60 nodes and one border router. So as we said, we have to ask the first question, how many nodes? So 60. How often do they send? Every 10 seconds. So that means that in 1 minute, the border router will be receiving 60 by 6 is 36 packets. So would that work? We can check the table. Even the maximum throughput settings can handle around 30 to 40 packets per minute. So 360 is way above that average, which means that unfortunately this will not be supported by receiver-based dish, and the user is better off using standard dish instead. Now let's examine another network with 30 nodes, so it's less than 60 UDP messages every 30 seconds. This will mean that the border router has 60 packets per minute. And again, when you check the guideline table, you will see that even with the maximum, which is 30 to 40 packets per minute, it's still higher than the capacity, and the user is, again, better using standard dish. Now, if we look at this third example with 20 nodes with UDP messages every 30 seconds, this will mean that the border router has around 40 packets per minute. And then when you check the table, you will see that this actually lies in the capacity of the maximum throughput settings. And then in this case, you can use the receiver-based dish. Of course, all these numbers in the table And the settings, they're assuming a normal and a good distribution of events. Like it can't be that all the 30, 40 packets are received in 1 millisecond, and then the remaining of that minute, there's no reception. Of course, at that time, everything will fail. So it's assuming a normal random distribution of the events and of the packets received. This chart, it shows for the previous example where that would lie around in the maximum throughput zone, so that actually can work. And here for our last example, if you have 20 nodes, UDP message every 4 minutes, this will mean that around 5 packets are reaching the border router per minute. And at that instant, you can even use the maximum battery settings, which can be used when you have a maximum of around 7 packets reaching the border router per minute. So then in this case, if you have 5, then you're very well in the range of the maximum battery settings. So to make things even more clear, we have here we plotted on the x-axis. It's the scale is logarithmic, but you can see on the x-axis we have the UDP interval, how often you send UDP packets. On the y-axis, you have the packet delivery rate, or the PDR. You can see that at very high intervals to the right, of course, the 3 lines are plotted for the 3 settings: the maximum throughput setting, the standard setting, and the maximum battery life setting. So on the right side, with very high UDP intervals, you can see that the 3 settings work. But as you can imagine, as the UDP intervals move from right to left, as the UDP interval gets more tight, like the more you send UDP messages, you can see that the first setting that will start dropping in its performance is the maximum battery, because it's not designed to handle much throughput. So it starts dropping, the first thing, and then the second one starts dropping, which is the standard, because it's merely a balance. The last one to drop, the last one to witness a degradation in the PDR, the one that can handle the most is the maximum throughput setting, the orange line, which, as you can see, it starts dropping at very tight UDP intervals. And these results are according to our simulations. So they are real numbers, not estimates. And this is designed for a 20 nodes network. Here on the x-axis, it's the same scale, the same UDP interval in seconds. And we have the 3 lines of the 3 settings that we have. But here on the y-axis, we have the average latency. And as you can see, the lowest latency is witnessed with the maximum throughput, as it's designed to receive and to move and to route more packets. So it will always have the least latency. And of course, the standard setting is the middle solution, which is always a little bit not as good as maximum throughput, but still it saves battery. And if you want the maximum battery settings, then you will have this, you can expect this average latency. So you can see that receiver-based TISH is designed for applications where you want to reach remote areas with battery operated, like your main focus is reaching very remote areas with battery operated mesh routers. You don't want infrastructure, you don't want to have them powered from a main power source. And having very small latency and having very high throughput is not in your concern. For example, a soil monitoring network in smart agriculture or smart irrigation applications. Soil soil monitoring, like soil moisture, for example, doesn't change every 30 seconds. So you don't need to send a packet every 30 seconds. If you send a packet every 10 minutes, every 20 minutes, then that's an example where a receiver-based dish would be very suitable. So I believe my part here is done. So Fruda, if you can hear me, I think the mic is yours, and I'm also here to answer some questions if my help is needed.
Yes, so please feel free to just post your question in the chat window if you have any, and we will try to answer them as good as we can. Okay, so I guess Omar made the point really clear. Now we got one question. What kind of frequency source, crystal or TCXO for hardware design? We do have that already in the module itself. It's a crystal, and it's a pretty good crystal, so you don't need to do anything in terms of compensating or anything. So that's already in the design.
Well, thank you, Faris, for the question. Thank you, Frederick. And as I said earlier, okay, we can answer this one first.
Yeah, we got a question about operating temperature, the range. I'll have to just look that up now. So hold on just a second. The operating temperature is minus 30 degrees centigrade to plus 85 for this.
Okay, so in case when you watch the webinar again, as you can download it, if you have any more questions, you can contact us at support@radiocrafts.com. So I guess that will be it for today. Thank you for taking the time to join us. Hope you gained something out of this, and have a good day.